1 here, but the cosmological constant pressure is minus lambda over 8 pi. So if we now think about the thermal energy of a black hole, one can, if the cosmological constant has an energy density associated with it, then that should surely contribute to the thermal energy. So the thermal energy should be not just the mass of the black hole, it should be the mass of the black hole plus the energy density times the volume. The energy density in the cosmological constant. So the vacuum has energy associated with it. But the energy density is minus the pressure. So the internal energy should be the mass minus pressure times the volume. The mass should be the internal energy plus PV. Now, if the internal energy U, as is usual in thermodynamics, is thought of as the function of entropy and volume, then this is Legendre transform. And the mass of the black hole is actually the enthalpy of a thermodynamic system. And this is what I'm going to go on to talk about in the second half of the talk. This is things that I've been working on for the last few years. The thermodynamics of black holes when you include a pressure term in the first law. Because up until this was sparked off by a paper by Castaway and Trasham 7 years ago, when they were the first people to point out that really you should think of the mass of a black hole as being not the thermal energy, but the enthalpy. Because if the cosmological constant is a fixed background, then the pressure is fixed, and the enthalpy is the correct thermodynamic function to focus on. Prior to 2009, no one ever included pressure and volume in black hole thermodynamics. So that's what I want to look at now. In ordinary thermodynamics, you can, if someone tells you what the enthalpy is as a function of pressure and entropy, then you can calculate the volume as being the derivative of the enthalpy. So I'm going to define this as being the thermodynamic volume of a black hole. Consider the mass of the black hole to be the enthalpy, write it in terms of relevant thermodynamic variables, entropy and pressure, then the derivative of the enthalpy with respect to pressure will be a volume. But from now on, I'm going to, for technical reasons, I'm going to restrict to positive pressure, because otherwise things are a little less well defined when the pressure is negative. The positive pressure corresponds to negative cosmological constant. So I'm going further away from any observational consequences here, because the real world cosmological constant, of course, is positive, corresponding to a negative pressure. But I don't want to. There are subtleties associated with negative pressure in black hole thermodynamics. I'm going to focus on the positive pressure case from now on mostly. I may say a little bit about negative pressure at the end of time, but I'll focus mostly on positive pressure. So if we work out the thermodynamic volume for a Schwarzschild black hole, then with a cosmological constant, a negative cosmological constant, so that means that very far away from the black hole, space-time is looking like anti-de Sitter space. So we take a Schwarzschild black hole embedded in anti-de Sitter space, work out the thermodynamic volume, you get 4 pi over 3 times the cube of the event horizon. Now, that may not look surprising to you, but if you think about it a little, it actually is very surprising. There's no simple way of defining the volume of a black hole. It's not, you cannot think of this as a geometric volume. For those of you who know the Schwarzschild line element of general relativity, inside the black hole, the radial coordinate is the time coordinate. So to take a little, say that the volume of the black hole is obtained by adding up the volumes of little shells inside the event horizon is utter nonsense. It's not a volume in any ordinary sense. In fact, inside the event horizon, the metric isn't even time independent. It's a complicated time-varying function, time-varying, funny kind of cosmology inside the event horizon. There's no accepted, well-defined way of defining the volume of a black hole in general. So I call this the thermodynamic volume to try and emphasize that there is no a priori reason why this should have anything to do with the geometric volume. And I have no idea why it looks like the volume of a sphere including space when you work it out for a Schwarzschild black hole, but it does. And this can be generalized. This is the ordinary four-dimensional result. If you go to d plus 2 space-time dimensions, then you get a result. So a result is very similar. So omega d here is the area of a unit d sphere. So this again is this is looking like the geometric volume of a sphere in d plus 1 dimensional space. Again, I emphasize that you should not think of the thermodynamic volume as being geometric. More complicated things were calculated by Sveti, Gibbons, and Kubiznak. They looked at higher dimensional black holes, Miles-Perry black holes, or rotating black holes in dimensions 4, 5, 6, 7, however high you want to go. And you can make them asymptotically anti-de Sitter. And these three people worked out the geometric volume for a rotating black hole in higher dimensions. I won't write down the general formula, it's a bit complicated. I'll focus on rotating black hole in 4 dimensions, because then the formula is fairly straightforward. If I define the event horizon radius times the area divided by 3 as being v naught, so this is like this would be the volume of a sphere in Euclidean space. Then the volume of a rotating black hole has a correction which involves plus j squared over m. It's a simple enough formula, but it tells us something very interesting, because it's saying that in ordinary Euclidean space, there's for spheres in Euclidean space, there's something called the isoperimetric inequality. If you take a sphere, for example, if you take a leather bladder so the area is fixed, and then pump it up, you get a perfect sphere. So if you fix the area and try and maximize the volume, the shape that does it is a perfect sphere. Alternatively, you can fix the volume and try and minimize the area. Again, the shape that does it is a perfect sphere. That's called the isoperimetric inequality in ordinary three-dimensional Euclidean geometry. Here, it's the other way around. The volume is minimized when j is 0, and j is 0 is a spherical shape. J is 0 is when the black hole is not rotating. So the spherical geometry is a minimum of volume. Right, so you fix the area, then minimizing the volume is a spherical geometry. So these people call this the reverse isoperimetric inequality. And as a consequence, I want to point out from this formula that as the angular momentum goes to 0, and we saw this in the reduction, the volume, well, I have the volume here, 4 pi over 3 r h cubed. The entropy, of course, is pi r h squared, the area of the event horizon. So this means that as the angular momentum goes to 0, the entropy and the volume are not independent. An isentropic process is the same thing as an isovolumetric process. That's not true when, in order to make the entropy and the volume independent of each other, you have to make the black hole rotate. And you can do that, but if we focus for the moment on the non-rotating case, we know the mass, so as a function of event horizon radius and cosmological constant, so we can write the mass as a function of entropy and volume. You can work out an equation of state, and this is the PV diagram for a Schwarzschild metric. So these are, I'm drawing here lines of constant temperature. It's pressure against volume for constant temperature. So we see up here, as the volume goes up, the pressure drop goes down. So that's intuitively similar to a gas. To the region to the left of the blue line, however, as the volume goes up, the pressure goes up. So that's a bit counterintuitive. This would correspond to a negative compressibility. So this, again, would indicate an instability in thermodynamics. A negative compressibility would be an instability. The fact that when the black hole is not rotating, isentropic process is the same as an isovolumetric process means that Carnot cycles in the PV diagram look like this. An adiabatic curve, a curve of constant entropy, is the same thing as a curve of constant volume, so they're vertical lines. So if you imagine taking a black hole through some cycle, a Carnot cycle, then it would look like this. So So to connect with concepts that you're familiar with, for an adiabatic curve, normally we write PV to the gamma as a constant, and of course we know that gamma varies, is different from monatomic gases to diatomic gases. If we write this as P to the 1 over gamma times V as a constant, then this kind of adiabatic curve is equivalent to sending gamma to infinity. It's saying that P drops out of this equation, it's independent of P. So a black hole is behaving as though it's got an infinite gamma. I mean, it's a non-rotating black hole. It's behaving like that. When you make it rotate, the PV diagram changes. These the regions of negative compressibility in the previous slide, remember these you went past these peaks and you just shot down to the origin. When you make it rotate, it's like almost like introducing a repulsive force, like introducing a centrifugal force into the PV diagram, and you no longer go through zero pressure for small volumes. In fact, this PV diagram does look rather like van der Waals gas. The PV diagram we get for van der Waals gas. I'm using here, what I'm doing is the angular momentum is 0, so I'm using the angular momentum to make everything dimensionless. So I'm using a dimensionless pressure in units of angular momentum and a dimensionless volume in units of angular momentum. And somewhere, I probably haven't drawn the correct isotherm on here, but somewhere between these two isotherms, so here we have a maximum, in the isotherm here, it's a function of volume, a maximum here, it's still a maximum here, and somewhere in here is a point of inflection. And that corresponds to a critical point, just the same as the van der Waals gas. If for temperatures below a critical value, there are two types of black holes, small volume black holes and large volume black holes, that can be in thermodynamic equilibrium. Above that critical temperature, there's only one phase.
Sorry.
Yes?
I'm a little confused because you shrink the radius in the innermost region, the pressure goes higher and higher. That means the core is becoming harder and harder. And how is the sound speed in the innermost region? In my imagination, the sounds, because if you have a very hot sphere and the sound transport very quickly outward, and the information should propagate more fast.
Yeah.
So
well, you can calculate the speed of sound, you can calculate the compressibility, you can calculate the speed of sound. It's never greater than the speed of light.
Not greater.
It's never greater than the speed of light. It's always less than or equal to the speed of light. But it's a sound that it's not a sound that's coming out of the black hole. It's more associated with the surface of the black hole. It's not true in 4 dimensions, but in higher dimensions, the black hole event horizon kind of ripples on it, and this speed of sound is. I'm not absolutely sure because it's difficult to calculate from first principles. But I think the speed of sound will be associated with the velocity of these ripples on the surface, but they will never leave the event horizon. So yes, you can calculate the speed of sound, and it's always less than or equal to the speed of light. If we look at the phase diagram for rotating black holes, what I'm plotting here is pressure against temperature, cosmological constant against the Hawking temperature. And then we saw in the previous diagram that you could have, if you're below a critical temperature, you could have large volume and small volume black holes. So here's a critical point. Again, in units of angular momentum, so everything's dimensionless. If you go above a certain temperature, then there's no longer a distinction between small and large black holes. But if you're below critical temperature and below critical pressure, then you can have a phase transition between small black holes and large black holes. This is a second order critical point. The latent heat vanishes. Once you come down here, the latent heat starts increasing, and there's a jump in latent heat across the line. And the critical point here is in the same universality class as the van der Waals gas. It has mean field exponents, same universality class as van der Waals. So we have this line of first order phase transitions with a critical point. This is identical to the phase diagram for van der Waals gas. You can check the latent heat, you can work out the latent heat, and indeed if everything works correctly, the latent heat is the temperature times the jump in entropy across the line as you go from small black holes to large black holes. The slope of this line, the PT plane, is given by the Clapeyron equation that if you work out the jump in entropy as you cross the line, you can also work out the jump in volume as you cross the line. And the slope of this line is the ratio of the entropy jump to the volume jump. That's the classical Clapeyron equation. So it all works for black holes. Interesting things happen in higher dimensions. In 6 dimensions, or in 5 dimensions as well, in fact, there are 2 angular momenta. For black holes in 4 dimensions, the event horizon is a 2-dimensional sphere. So the largest symmetry you can have is SO3 symmetry, and there's only 1 angular momentum associated with it, with SO3 symmetry. If you go to 6 dimensions, then the black hole would have an event horizon which would be a 4-dimensional sphere. A 4-dimensional sphere has a much larger symmetry than a 2-dimensional sphere, and there are 2 angular momenta, 2 independent angular momenta associated with the 4-dimensional sphere. And the phase diagram depends on the ratio of these 2 angular momenta. So this was the phase diagram for a 6-dimensional black hole was worked out by these people just last year. This is all done numerically. The previous stuff was analytic. In 4 dimensions you have to do it in the computer. And they found a phase diagram that looked like this, and it's got much more intricate structure than 4 dimensions. We see that there's 2 critical points. There's a region here where there are 3 sizes of black hole. You can have small, intermediate, and large. And then, so this is a critical point here. This is a line of first order phase transitions. There's a critical point here, but a line of first order phase transitions. These 2 merge at a triple point here, and below this is only a single line of first order phase transitions. So we can, in 6 dimensions, we have not only critical points in first order transitions, there are also triple points in the black hole phase diagram. There are also examples of re-entrant phase transitions where you go from one phase to another and then back to the original phase just by changing a single parameter. So in higher dimensions it gets quite rich structures. So I've already said that. There's examples of re-entrant phase transitions in higher dimensions as well. Okay, I now want to address the question of stability. Probably going to run out of time, so I should be thinking what to cut out. Okay, we have a few minutes left. Let me try and I mentioned earlier that so far I've emphasized the similarities between black hole thermodynamics and ordinary thermodynamics, but there are also differences. There are strong differences in certain directions. In ordinary thermodynamics, entropy is a function of extensive variables. So the entropy would be, you could describe your system in terms of entropy, which is a function of internal energy, the volume, and the number of particles, for example, for a single component gas. So I'll write generically denote the extensive variables by Xa. And local thermodynamic stability would demand that the entropy is a concave function of its arguments. So if we work out the matrix of second derivatives, then that should be a negative definite matrix, or the negative of this should be positive definite. I mean, so all the eigenvalues of this should be positive numbers. That's necessary and sufficient for thermodynamic stability. Alternatively, we can use the internal energy as a basic thermodynamic function, and that will be a function of entropy volume, and that should be a convex function. So we can use either the entropy or the internal energy, depending on which is more convenient. The intensive variables are the Legendre transforms of the extensive variables. So the Legendre transform of entropy is temperature, the Legendre transform of volume is pressure, actually minus pressure, and the Legendre transform of the number of particles is chemical momentum. These are intensive. if we scale, everything scales like volume. This goes back to the question we had before. If you double the volume, double the entropy, and double the number of particles, then you should increase the internal energy by 5.2. So all the extensive variables all scale the same way. If you increase the length scale, so lambda here is the length scale. D's are little d's are dimension of the system. So if we take this equation, you differentiate with respect to lambda, then put lambda equal to 1, you get this relation here between the various thermodynamic variables. This is always true for any classical thermodynamic system. And in fact, this is essentially what's called the Gibbs-Duval relation in classical thermodynamics. In particular, one thing that textbooks in thermodynamics never do is that they never Legendre transform on everything. Because if you did, you'd get 0. If you decided you were going to Legendre transform on all 3 variables, and instead of using U, I was going to use a thermodynamic potential which depended on the 3 intensive variables, PT and U, then you Legendre transform on all 3, and because of this relation, you just get 0. In classical thermodynamics, no one would ever dream of defining a function which is a Legendre transform of all the extensive variables. They always keep at least one extensive variable there. Otherwise, you've thrown away everything. Now, for black holes, the scaling doesn't work. What is an extensive or an intensive variable for black holes? It's not obvious. In ordinary thermodynamics, temperature is intensive. You take some mass of gas, this constant temperature, break it up into 2 halves, the temperature doesn't change. So the temperature doesn't depend on the size of the system at all. It's intensive. You cannot break a black hole up into 2 halves and have 2 systems both at the same temperature. It's not possible. So it's not obvious how to define extensive and intensive for a black hole. So I'm going to make a proposal. If we work out the dimension of the various quantities for black holes, work out the mass, the entropy, the momentum, the volume, and all the other things we want to have. If you set speed of light to 1 and use Newton's constant to turn masses into lengths, so Schwarzschild radius becomes Schwarzschild mass, then you can work out the dimensions of all of these things, the scaling dimension of all of these things, and they depend on the dimension of space-time. Capital D is the dimension of space-time. So for a space-time dimension capital D, the entropy, the area of a black hole has dimension T minus 2. So you take a space-time dimension, you throw away time, you throw away the radial coordinate, you've got a T minus 2 dimension. So in 4 dimensions, the event horizon is a 2-dimensional sphere in dimension 2. But in 5 dimensions, the event horizon would have dimension 3, and so on. So you can work out all of these, the scaling dimension of these various physical properties of black holes, and I would propose that the quantities whose scaling dimension depends on the dimension of space-time should be considered to be extensive. And the quantities whose scaling dimension is independent of the dimension of space-time, I'll call extensive. That's just my definition. You can disagree with it if you wish. There's no accepted definition in literature of what extensive and intensive is for a black hole. But I think this is a reasonable working definition. Notice that the extensive variables, they have different scaling dimensions. In ordinary thermodynamics, all extensive variables have the same scaling dimensions. And now this is quite important. There are textbooks written in thermodynamics where one of the basic axioms is that the scaling is all homogeneous. So it's an open question as to what kind of consistent thermodynamic systems you can make where the scaling dimensions are not homogeneous. I think it's an interesting question. I believe that black hole thermodynamics makes sense, so I believe it ought to be possible to construct a consistent thermodynamic system where the scaling dimensions are homogeneous. But no one has done it on any axiomatic basis as yet. Okay, so that's what I'm going to do. I'm going to define the extensive variables as those that depend on the space-time dimension. So now let's look at scaling for black holes. I said the entropy scales as the space-time dimension minus 2. The volume scales as space-time dimension minus 1. So this is the volume of space. Excuse me, it should be an omega there. That should just be J. The angular momentum scales is T minus 2, and the electric charge scales like this. And the mass of a black hole always scales like T minus 3 in space-time dimension capital D. So this T minus 3 is associated with dimensions of Newton's constant in T space-time dimensions. So we can do the same thing as before. We can differentiate with respect to lambda and set lambda equal to 1, and we get a relation between the various, one relation between the internal energy and the products of all the internal extensive variables. So these D's here are just numbers that you can work out, the ratios. Capital D minus 2 or capital D minus 3. So then we can work out the complete Legendre transform. Let's Legendre transform on all 4 extensive variables and construct a thermodynamic function, which is intensive variables. And when you do that for a black hole, you get an answer that's not 0. In classical, in ordinary thermodynamics, you just get 0. In black hole thermodynamics, you don't. This is non-trivial, and this should be checked. If this is going to make sense, this should be checked against known solutions of Einstein. For rotating black holes, I gave you Hawking's formula. You can work out the area of the event horizon. You know the mass and the pressure. And these are things that are given that you can work out in explicit solutions of Einstein's equations. And it is not an a priori given that this relation will be satisfied. It's something you have to check. But it works in all known solutions of Einstein's equations. And even in theories of gravity that go beyond Einstein's equations, like log C. So this relation is always satisfied in all known solutions. Now this combination of functions here, the internal energy plus PV, remember that's the enthalpy. If you didn't have these here, if you just had U plus PV, that would be the enthalpy. So that's the black hole mass. And indeed, if you take the full Legendre transform here and work out this, so you know you can work this out because you know the black hole mass, you know the Hawking temperature, you know the area of the event horizon, and in any given solution you can work these out as well. And what you actually get is the same thing as Euclidean action for quantum gravity. The complete Legendre transform, this function of intensive variables, is the same as the action for general relativity on your black hole solution. Except if you Wick rotate sends time to complex time, you send t to it. You use Euclidean time. Work out the action of the system. This is the thing that appears in people's path integral approach to quantum gravity, is this Euclidean action. It's precisely this Legendre transform. So this hangs together and makes sense for black holes, even though the scaling is not homogeneous. I think I might skip this. Yeah, let me quickly skip this. And I'm running out of time, so I'll just maybe spend a couple of minutes on global. What I've discussed mentions, well, I mentioned the second derivative of the internal energy should be a positive matrix for local thermodynamic stability. Of course, black holes, we know that for a Schwarzschild black hole, the heat capacity is negative, so the condition for local thermodynamic stability is not satisfied by black holes. Though there's still very interesting thermodynamic systems. But we should also ask about global instabilities. And in 1983, Hawking and Page pointed out that there was a global instability against black hole decay. And if you take a black hole in asymptotically anti-de space at a given temperature, so you can work out use the Hawking temperature to work out the temperature of the black hole, and just compare that to empty space, anti-de space, but with thermal radiation in it, then if the free energy of the black hole is less than the free energy of empty space, the black hole will be stable. But if the free energy of the black hole is greater than the free energy of empty space, the black hole will be unstable.